back. So in the previous example, we saw how the function g is the area so far function is defined. Here is another concrete example. Consider the function ft equals t. Okay, you can think of it as y equals t. Start at 0. Find the area so far from 0 to x t dt. They are saying it's x squared over 2. Let's figure this out. It's actually quite trivial. So here is your graph, y equals t. Okay. If you take a number x here, you're going to get coordinate xx. I hope this is clear. So this is the function y equals t. So it is the diagonal line for t-axis versus y-axis. Notice we are used to calling it y equals x, but I'm simply following the function given to us, ft equals t. T is the independent variable. Now as x changes, the area under this curve will change, right? So x is somewhere here. So let's find the area here. What is the area? This is a triangle. Base x, height is also x because that's the definition. When it's t, it's tt. When it's x, it is xx. When it's 2, it's 2, 2, 1, 1, 1, and so on. So, area from 0 to x is half base times height, x times x. So, half x squared over 2. All right? Sorry. And on the other hand, so this is your function gx. On the other hand, notice if I take derivative of g, that 2 comes down, cancels the 2, and I get x. So in other words, when I take the derivative, I get the function inside. Okay? Function inside, of course, with x replacing t. Okay? G is defined as the integral of f. Then g turns out to be the antiderivative of f. At least in this case, okay? That is the fundamental relationship between integral and derivative. All right. So, and if we sketch the derivatives of the function g, we will get a graph like in figure 2, right? So, why this might be generally true, we consider any function f. This is a good result. Assume your f is greater or equals 0. Let g be the function area so far. So as x changes, my area will change. Okay. So gx is the integral a to x ft dt. Okay. It's area under the graph of f from a to x. All right. Now here is the catch. In the previous case, we looked at derivative. So that's what I'm aiming for, right? So in order to compute derivative, how do we compute derivative? So let's see. For an h positive, you're looking at g of x plus h minus g of x. What is the meaning of g of x plus h minus gx? If you remember, this is how you get derivative. Gx plus h minus gx over h as limit h goes to 0. So let's pick up pieces of each one, right? G of x plus h minus gx. So area until x plus h minus area until x. So from a big area, take away the small area and you're left with this small area. This small sliver is area until g plus x minus area until x. All right. Now, so g of g plus h minus g of h is approximately h times fx. Does that make sense? H is the width here and fx is this height. So it looks like this area under this small curve is approximately area of this rectangle. Width h, height fx. approximately so. So why don't I divide by h? So gxh minus gx over h is approximately fx. When I take limit h approaching 0, on the one hand I get derivative, on the other hand, because this no longer has an h, limit continues to be fx. In other words, derivative of the area function is the original underlying function. Okay, which brings us to part 1 of the fundamental theorem of calculus. Notice our description here, we required f to be positive, but this fact is true even when f is not necessarily positive. If f is continuous, continuity is important. If f is continuous on closed interval ab, then the function g defined by gx equals integral from a to x ft dt for any x between a and b is a continuous function. It is also differentiable on open AB with the derivative equals f of x. The underlying function is the derivative of the area function. In other words, using Leibniz notation, that is, instead of prime, you would say derivative of the area is the underlying function fx. Notice x evaluated at the last point, upper limit. All right. That is the first part of fundamental theorem of calculus. This equation says that if we first integrate f and then differentiate, we get back the original f. Okay. I must emphasize f of what? It's not f of a, f of the final limit, upper limit that goes out here. All right. So here is an example. Let's come to the example in our next video.